Hello dear friends, welcome to my channel. Today's discussions is introduction to field equations. To cover the Klein Gordon field and the Dirac field, we are also going to discuss Maxwell equation to make additional progress in this area, quantizations of electrodynamics. So let's start conventions. Now G mu and G mu is a metric, okay? Metric, and this is the matrix whose diagonal is 1 minus 1, and it can be written as eta mu x. X is a point, any point. Now let us discuss this function. We need to know a diagram. This is the diagrams. A homeomorphic morphic to manifold, a four dimensionals. Four dimensions means r to the power 4 dimensional. Every time space time can be labeled. We need the conversation of the space time. This is the eta mu. We need to the convention. We need to the convention. So it's in the absence of gravity, because this is the quantum field. Quantum field is absence of gravity. This mapping is homeomorphic. We can create physics on the abstract space of reality by studying this abstract space of a four-dimensional manifold. When I say abstract space of reality, that sounds kind of weird. It is modeled by a 4D manifold. This is the 4D manifold. 4D manifold. Create our models in four-dimensional space. Any point of four-dimensional space. So any point of four-dimensional space is, this is the point, this is the x, this point is this. Four-dimensional space, for example, it finds some kind of number. I should say x, and it can be r, and c. For complex numbers, complex class assigns a complex number, and if it assigns a real or complex numbers, we are going to call the field scalar. This is a scalar field, that is Ex and Ey and Ez. Ex, Ey, Ez. It could assign a no it could assign a no-kidding vectors, right? We could vector at this point. We have studied this a lot in spinor and tensor and all kinds. Scalar field are a little different. You could imagine, say, fluid. This is the mathematical model. Phi is a scalar field. Phi is a scalar field. We are going to say the space-time point is x, and x is stand in x0, x1, x2, x3, and phi x mu, phi x mu, because would almost imply that there are four phi functions. Phi x mu is the conventions. It can be written as four functions, that phi x0, phi x1, phi x2, up to up to four terms, and real or complex scalar field. So Lagrangian, what is my Lagrangian? I'll go to the next function. Okay, another factor is we need ex, uy, ez is the vectors, and we know that we know that the force F equals to Q into E. This is the formula, and this is the U. So eta mu nu. Now Lagrangian is the field derivative with respect to time. What is the Lagrangian? Let's go to discuss Lagrangian. Now friends, Klein Gordon theorem, Gordon field, Lagrangians is a action, means S. Okay, is for action, and this action is minimize the action gives us the equation of motion. Klein Gordon field is basically the scalar field that follows from this Lagrangian equation. This is way of approaching the motion of Klein Gordon. It is classical field. Klein Gordon is classical. This is the classical Klein Gordon classical field. Okay, this is the classical field. Lower dummy index del mu. Okay, lower dummy index, this is the lower dummy index is del mu is a positive. Mu is positive, and upper dummy index is negative. Okay friends, and this is the spatial derivatives. This derivative is called spatial derivatives. Now del L by del phi is equal to m square phi. Care of this piece, right? So del L by del phi is equal to m square phi. Okay, stands for del L by del phi, it stands to m square phi. And first partial derivative of phi Lagrangians, this is the first partial derivative of phi. Phi Lagrangian is function of gradient. So it is the Lagrangian, the function of gradient, and you must remember this is the function of gradient. So it is derivative by gradient, and this is metric. This portion is metric. Okay, this is metric which I have already discussed in. Okay, you will see that this matrix is equivalent to this matrix. Okay, a mu in here alpha beta. Now L equals to del phi b del beta del phi. This is the L. This is the Lagrangian. Okay, so this value we just putting the L equals to del mu del phi, this value, and this is the metric, and putting this value, this metric value, this metric value in here, this is the metric value, and that is the contravariant. This is the contravariant vectors, this is the covariant vectors, and this is the contraction. This portion is contraction lower vector. Okay, contractions, this is the upper and lower. This is the contractions, combined time derivative part of the space derivative part. And in here m is, where is the m? L equals to this m. M is the m, meaning of the m is a parameter. M is a parameter. M is parameter, and this is the gradient phi, grad phi dot whole square. L equals to half into phi dot whole square minus half into del phi whole square minus m square by phi square. So when with respect to derivative with respect to del mu phi, so it can be written, okay, in here it is writing, in here it should be mu. Okay, and it is not correct, and it is also mu. Okay, and so it is the half into eta alpha beta del into del alpha phi del into del mu phi del phi del beta phi, and half into eta alpha del alpha phi is equal to del beta phi del. So this term is become Ronecker delta. Okay, this is the Ronecker delta. Ronecker delta is, we know this Ronecker delta can be written as beta mu, and this Ronecker delta can be written del alpha mu. So you see this mu, this alpha index and this index is cancelled, cancel, so I replaced this mu in here, so I get arise this mu beta and del beta phi, and this one delta is multiply, so del alpha beta beta cancel, beta and this beta is cancelled, so half into eta alpha mu del alpha phi. So this total multiplication is this can be written as del del this is the delta functions, so this can be written as del mu into del upper del mu means del subbase mu and del mu super base, okay, superposition, so it is del mu. So del mu is equal to m square is a Gödel. This is the Gödel equations. This equation is called KGF. KGF equation. Okay, means Klein Gordon equations. Now, friends, we start talking about conservation's law. So we are going to special theorem of relativity. Okay, now we discuss this is the KG equations for relativity. In case of relativity, we see that E square is equal to P square plus C square plus M square C to the power 4. This equation I have already discussed in my string theory videos. Those who are watching, they know that this is the very important formula and it can be written this way. Now I use quantization. What is the quantizations? First quantizations I used. This is value of the E equal to I h bar. H bar is equal to Planck constant. So h bar is equal to h divided by 2 pi, where h is a Planck constant, Maxwell Planck constant. So this h bar is the h bar, and I apply in here, putting the E is equal to this value, so I get I h square del 0 square minus I whole cube h del bar whole square c square, just putting the p square values. Okay, and m square c to the power 4 pi, and now pi I just taking common pi, so I get del square. This is the equations. So I must remember I discussed first quantizations. What is the first quantizations? Now it is very important. First quantizations, E for energy and P, and the momentum operator is always momentum operator. This is the momentum operator. This is momentum operator. This is negative. Momentum operator. This is negative, and this position is the fourth dimension space time. This is the fourth dimension space time. So contravariant operator, this operator is called contravariant operator. Now I apply this quantization in here, I get KG equations from relativity. Now next I will go to discuss complex operator Klein Gordon. Okay, before the complex operator, I need to discuss Klein Hamiltonian operator. Gordon Hamiltonian. So P bar P is the momentum. The classical mechanics we use. P is a momentum. Del L by del Q dot is equal to del L divided by del 0 Q, and del divided by del 0 phi. Del 0 phi means gradient phi, and gradient phi whole square, just putting the value of the Lagrangians, and pi x is equal to phi dash dot x is equal to del 0 pi x. And we know this formula very well, that h is equal to pq dot minus l. So when I use that pq dot, then the value is coming d cube x divided by phi dot and half phi dot square. So our equation is d cube capital X half sigma pi capital pi dot square capital pi dot square pi square plus del means nabla phi plus half into mu square phi square. So we remember we have to create a conjugate momentum associated general coordinate. We take that phi t0 x is equal to phi tau comma x. So friends, now we discussed complex kg field. So complex kg field, we can write L is. Now friends, we discuss complex Klein Gordon. L equals to half into del mu phi 1 del mu phi 1 minus m square divided by 2 phi 1 square, and into del mu phi 2 minus m square divided by 2 phi 2 square, and thus only the simplifications, the subtractions, general subtractions. So we can get it through the minus I phi 2 minus I phi 2, and this is the I phi 2. And now you have to must remember that these positions, this is called phi plus. So I am putting in here phi plus, and this is the general phi, and this is the phi plus. So we get 5 conjugate Heideggers. So 5 conjugate Heideggers means we get another equation. That equation I write down in here, that del mu plus m square phi equals to 0, phi 1 equals to 0, and del mu plus m square phi 2 equals to 0, and del mu plus m square equals to 0, and del mu del mu plus m square phi equals to 0. So this is the my 5 Degas equations. Now we discuss Klein Gordon no either current for space time. So let's start that T mu nu. This is the formula that in case of electrodynamics, that T mu nu equals to del L. The gradient is del, and del mu phi, and mu phi minus L del mu nu. This is the gradient, okay, gradient phi. So derivative of the gradient phi, so it can be written as T mu nu is equal to del mu phi and del contravariant tensor del, and this is the covariant, and due to the contrast, and another is that minus half means L value del mu v, so it is half into del beta phi into del beta phi minus half m square phi square del mu nu and T mu nu equals to the metric tensors eta nu beta del mu phi into del nu phi, and Hamiltonian H equals to T00 d cube x equals to phi dot whole square minus half phi square minus half into gradient phi whole square minus half m square phi square d cube x, and pi means momentum tensor is T0 dx equals to integration eta alpha beta del 0 phi d dx cube. So this can be written as phi minus phi del I del I high is equal to minus integration del I high d cube x. So del mu phi equal to gradient phi. So I hope friends I can explain something little about Klein Gordon field equations. So this is very important for quantum field theorem. So what is quantum field theorem? Quantum field theorem is where gravitation is not present. In here electric field, electric magnetic field is present, weak strong interactions and weak interactions is present. Thanks for watching. I will create a lot of videos based on quantum field theory.